So section 12.3 works with geometric sequences, and the first thing that we're going to look at is the first 5 terms of this sequence, and we'll talk a little bit about it in specific and then in general. Now, if you're just asked to list out, the first few terms, you can do it by hand, and that's fine. But let me remind you how to do it on a graphing calculator. So, fire up your graphing calculator. In fact, maybe I'll do it this way. Come on, open. There we go. Somebody have to give me some feedback if it's easier to see things here or not. Yeah, let's clear the history. So, to get a sequence or a list of terms in a sequence in your graphing calculator, what you can do is hit the second key, then the stat key. That'll take you to an operation or to a menu like this. Cursor to the right once. It says Ops. And then we want the 5th selection down. So either scroll down and press Enter or simply type the 5. Now for me, this is menu driven. If it's not menu driven for you, then just hang on a second. You're going to type in all this information. But what we want to start with is the expression here. So let me just clear that out. And I want to type in 6 times parentheses negative 0.5 raised to the n-1 power. Now, the way it's given to me like this, I have to be careful and put my exponent in parentheses. So it would be parenthesis n-1. Now, if you're getting an x when you hit this key, that's okay. You're just in a different mode than I am. This one happens to be in sequence mode. That's okay. Let's scroll down. The variable that you're using here is n. For you, it could be x. You're going to start the first term, end with the 5th term, and increase by 1. Now, if your calculator is not menu-driven, then just hang on a second. Go down to the bottom here, press paste. If your calculator is not menu-driven, then you're just simply going to type in what we have here with commas that you can find right above the 7 key. And that should list out the first 6 terms. First 5 terms, I should say. So there you go. We got a sub 1 is 6, a sub 2 is negative 3, a sub 3 is 1.5, or you could also think of that as 3 halves. A sub 4 is negative 3/4, or negative 0.75, and a sub 5 is 3/8, or 0.375. So, nice. So those are the terms in your sequence. You could sum those up if you wanted to. I'll give you a quick thing on that. If you hit the second key, then catalog. Let's press the number 4, which jumps us up to the T's, and then go backwards to sum. Not summation, but sum. We can sum our previous answer, second, and then the answer key. Sum the previous answer gives you the sum of those things. So great. A little bit more than we may have needed, but not too bad to review some of that stuff. Let's get back to this, though. Here are the terms. And what you could notice is that to get from one term to the next, you're consistently multiplying by what? Close. Negative 1/2. By negative 1/2. So that makes this a geometric sequence. That is, to get from one term to the next, you're multiplying by the same thing again and again and again. And that same thing is called R, which is your common ratio. The general term in your geometric sequence looks like this. A sub n is a sub 1 times r to the n-1. R, that's what you're multiplying by to get from one term to the next. R is, like I said, the common ratio. What's a sub 1? 6 in this one. Yeah, it's the first term. So So you start with your first term and then you keep on multiplying by r to get subsequent terms. All right, nice. You can check what the common ratio is. Now, I like to think of r as being what you multiply by. But from this definition or this verbiage here, it's the common ratio. And you can see that it's a common ratio if you do this. You take a sub 2 and divide it by a sub 1. So negative 3 divided by 6, oh, that's negative 1/2. If I go to the third and second terms, a sub 3 divided by a sub 2, that's going to be 1.5 divided by negative 3, and again, I get negative 1/2. Anywhere in this sequence, if I take adjacent terms, divide the former by the prior, I'm always going to get that same ratio. That's why they call this the common ratio, because it's the same for all these terms. So we're looking okay on the first one. Problem 6. Yeah. The comma or the which button you're trying to look for? It should paste in the commands for you when you do that. If it's not, which calculator do you got? 84? Okay. If it's not, maybe it might not be in math print mode, or you might have something, you might not have your calculator up to date in terms of its operating system, but when you fill this in, it should work. So let's see. This is one we're going to use later. Variable n. Yeah. So I'm not sure. I have to take a look at your calculator to see what's going on with that. You know what? There is one last thing that they ask you to do here, and that is to graph your sequence. So let's graph this. The graph's not going to be that exciting, but it's still something that we should be able to do. So to graph it, let's actually take the time to put our calculator in the proper mode. And Sam, maybe this will help you out a little bit. So we'll see. So hit the mode key, and then go all the way down and over to sequence. Press enter with the highlight on sequence so that your calculator is now in sequential mode. What that's going to mean is that instead of getting an X when I type this key, I'm going to get the N. All right. Let's go up to the Y equals key. If you go up to the Y equals key, you can type in your new function. You're going to see something much different in this menu than you usually see, right? You see N min, you see the place for your expression, etc. So let's type in 6 parentheses negative 0.5 raised to the n minus 1 power. Let's graph, say, the first 10 of these. So we'll see what that looks like. What you should do to graph the first 10 of these is set up your window from n equals 1 to 10. Now, if you want to do n equals 1 to 8 or 6 or whatever, that's fine as well. But choose n equals 1 to something, and then let your calculator do the rest. Hit the zoom key. Zoom 0 will fit your calculator's window to this graph. So zoom 0 gives you something like that. And the nice thing is if you hit the trace button, you'll be able to see some of these numbers. So there you go. So that's the graph, and that's kind of it. That's the last part of problem 6 is to graph this. Now some of these get really, really small, and eventually you can't really distinguish these from the x-axis. It is what it is. Let's work with these things in general. And for that, I'm going to look at problem number 10. Problem 10 asks us to find a geometric sequence or the general term of geometric sequence with a sub n equals -3 and r equals -2. Okay. Well, they're kind of giving us everything we need here, right? We know that a sub n equals a sub 1 times r to the n minus 1. So it'd be -3 times what? -2 to the n minus 1. Okay.
That was easy.
Yeah, I'm afraid that's it. That's all there is to that one. So, nice. Let's try some other ones, maybe a little bit more challenging, where we have to think through these problems and decide, well, is that a geometric sequence or no? So we'll start with problem number 14. So our problem there is 3, then 48, then 93, 138, etc. At the same time, we got problem 16 is 432, -144, 48, -16, etc. So the question is, are these geometric sequences? Let's take a careful look at 14. If this is a geometric sequence, I have to multiply the same thing to get from one term to the next. So in this case, well, you can kind of do it in reverse. 48 divided by 3 is 16. If I multiplied 16 times 48, am I going to get 93? I don't think so. In fact, this is a different type of sequence altogether. Does anyone recognize that sequence? Can anyone tell me how I would get the next term here? Add 45. And if you're adding something to get from one term to the next, what kind of sequence does that make this? Good, arithmetic sequence. So in this case, a sub n would be a sub 1 plus n minus 1 times d. So it's going to be 3 plus n minus 1 times 45. That's going to be your general term. But that makes that an arithmetic sequence, not a geometric sequence. So in a geometric sequence, you're going to multiply to get from one term to the next. What about here? Am I multiplying to get from one term to the next? Let's take a look at adjacent terms. -144 divided by 432, or 48 divided by -144. You can take out your calculator and work on these things if you want. You should get the same decimal value for each of these, -0.333333. Thank you, -1/3. -1/3. So it does appear, in fact, you can try it one more time. 1/3 of this is 16. Account for the negative, you get -16. So it does appear that you are multiplying by this common ratio to get from one term to the next. So this is geometric. And the question is, what's a sub n? All right, 432 times -1/3 raised to the n minus 1 power. Nice. Let me give you a couple more like that to think about. Problem number 20. E squared, e to the 4th, e to the 6th, e to the 8th. And 22, 1/2, 1/4, 1/6, 1/8. The question for both of these, are these geometric sequences? Try and work on those. Figure out if these are geometric sequences or not. If they are, write down the general form of that geometric sequence, much like we did in problem 16. What you should be doing is looking at the common ratios. See, are you multiplying the same thing here from one term to the next? So you can divide adjacent terms. That's fine. So no, I don't want this. Use whatever should is. You should be able to give me a nice expression for that. What you should be doing is looking at adjacent terms. So e to the 4th divided by e to the 2nd. I hope you didn't take out your calculator, because you can just subtract the exponents. You get e squared. Let's try another pair of adjacent terms. Say these two. E to the 6th divided by e to the 4th. E to the 2nd. So it's the same thing from one to the next. So that's your common ratio. That's r. And to finish it off, we'll write it as a sub n, a sub 1 times r to the n minus 1. Now this one's going to get a little tricky. All right, but I'd like to see it written like this. What's a sub 1? E squared. What's r? E squared again. I'm happy for you to leave it like this. There's nothing wrong with it. So that's your a sub n. It is geometric. You could, if you played with it, simplify it to e to the 2n. Nothing wrong with that. The only thing is, I like it here because I can look at it and say, okay, that's the first term and that's the common ratio. So, there we go. Are we okay with problem 20? Yes. It's not arithmetic, because you're not adding the same thing to get from one term to the next. If you looked at those terms, they don't form an arithmetic sequence. So you could look at, say, e squared, e to the 4th, e to the 6th, and there's not a common difference between these. You're not adding the same thing to get from one to the next. But if you divided two of these, if I divide this one by, say, this one, I should get the common ratio, which is e squared. Whoops. Delete that. There you go. Yeah, and that's your e squared. Okay. How about problem number 22? Are you multiplying by the same thing to get from one term to the next here? No. You should be able to convince yourself of that pretty quickly. If you look at the first pair of numbers, 1/4 divided by 1/2 simplifies to 1/2. Whereas over here, these two numbers, it'd be 1/6 divided by 1/4 turns into 4/6, which is 2/3. And these are not equal. So you don't have a common ratio that you're multiplying to get from one term to the next. So not geometric. And that's really all you got to decide, is whether or not this is geometric. Yes.
The e to the 2n is geometric, but 1/2n isn't?
Yes. Yeah, it's kind of funny. So the general term here, Andy's noticing, is this. This is 1/2n. That's not a geometric sequence. But the general term here, e to the 2n, is a geometric sequence. So yeah, it is kind of funny that they have the expression 2n in both of them. One's not geometric and one is. So yeah, nice observation. Let's try problem number 30. So kind of similar to the previous couple, except this time you are going to be working with geometric sequence. I always kind of pause a little bit because I want to say series. Series is when you add up the terms in the sequence. So that's going to be 28/9, and then 56/27. So there's a couple things that I want here. I want to know what the fifth term is, a⁵, and I want to know what the general term is. So those are the two things I'm looking for in problem number 30. So probably would help out to figure out what the general term is next, and then go back and figure out what happens when we plug in n=4 or n=5 to get the fifth term. Start by trying to find r. Okay, so the general term is a⁵ times r to the n-1. We already know what a⁵ is. That's over here. That's 7. But we need to figure out what r is. So let me help you out with that calculation. And there's a couple ways you can do it. You want to divide this term by the previous term, or this term by the previous term. The cool thing that you can do, especially if you have a nice up-to-date calculator, is hit the alpha key, alpha, y=. The first one down gives you a fraction. So I'll take 14/3 divided by 7. If you do it that way, I think it should automatically put it in a nice fraction for you. Yay. Now, if you're not into that, you can just simply do 14 divided by 3 in parentheses divided by 7, and then hit the math key, answer the fraction. So, okay. Let me try that once again with these two to make sure that it's the same ratio here to here that it is from here to here. So that would look like, let's see, 28 divided by 9 divided by 14 divided by 3. And again, it should give me a nice, neat fraction. Sweet. 2/3. So, pretty confident that r equals 2/3. And with that, we can come up with a sub n. A sub n is 7 times 2/3 to the n minus 1. Now, there's two ways you can come up with a sub 5. One is you can put a 5 in here, and then just do it out this way. But keep in mind what that common ratio says. To get from one term to the next, I'm just multiplying by 2/3. So this times 2/3, this times 2/3. And that's not too bad. What's 56 times 2? 112. And 27 times 3? 81. Thank you. So, there you go. How are we looking on problem 30? Okay there? All right. Let's do a similar one to that, or not. It's up to you. Are you good with that one? We can do another one like that, problem 34, or I could move on to other things. What do you want? A question on that one first? Well, you could do something with the n minus 1. This is the general term, so I got the fifth term by just realizing, okay, you keep on multiplying by 2/3. I wanted to minimize my thinking is what I did. If I wanted to, though, or if I needed to, I could say a sub 5, that'd be 7 times 2 over 3 to the 5 minus 1, and that'd be 7 times 2/3 to the 4th power, which is, what, 16 over 81, and 7 times 16 would be 112 over 81. So yeah, you could use it or not. It's kind of up to you what you find most convenient. I just found it easier to multiply that by 2/3. But some of these problems, obviously, it'd be a pain. So it's nice to be able to do both. All right, thank you. Was it an A or an A on problem 34? Want to do another one like this or no? All right, I heard enough yeses that I want to do one. So we'll do problem 34, -8, -2, -1/2, and -1/8. So similar kind of thing on that one. Let's see if we can't just determine the general term here. That's all we're looking for is a sub n. Okay, so same kind of game as the last one. You want to look at adjacent terms. if I take negative 1/2, negative 1 divided by 2, and divide that by negative 2, I get 1/4. And then negative 2 divided by negative 8.25 is also 1/4. So pretty confident that r equals 1/4. There's your a sub 1. So negative 8 times 1/4 to the n minus first power. All right, not so bad. Not so bad. Feeling a little bit better about these? There's a few people that were uncomfortable. So, okay. Let's move on to problem number 42. Let's see. 2 and problem 42. You're asked to find the general term of a geometric sequence, and they tell us just a little bit of information. They tell us that a sub 4 is 12, and a sub 7 is 32/9. Wow. Looking kind of ugly there. And somehow from this, we're supposed to deduce the general term. A sub n equals a sub 1 times r to the n minus 1 power. Well, there's two things that we don't know here. We don't know a sub 1, and we don't know r. So those are the two things we don't know. But since there's two things we don't know, we're hoping that we have a way to come up with two equations. And we do. Here and here. This should help us come up with two equations. Two equations for two unknowns. A nice symmetry there. Let's see what the first equation is going to be. It's a sub 7 equals 32/9. The other one is a sub 4 equals 12. So let me type in this one first. So 32/9 equals a sub 7. Doesn't look like it. It looks like a 9. Sorry. 9 sub 7. A sub 7. But what's that going to be over here? It's going to be a sub 1 times r to what power? 6 power. Let's do the same thing for this one. 12 equals a sub 4, which is a sub 1 times r to the 3rd power. Right? Because 4 minus 1 gives me the 3 there. And that doesn't look too helpful at all. But there's a little bit of a trick here that I'm going to share with you. Something we can do. Because remember, we're going to use these two equations to solve for a sub 1 and r. So here's the trick. We're going to divide these two equations. I'm going to take 32/9 and divide it by 12. And that's going to equal a sub 1 times r to the 6 divided by a sub 1 times r to the 3rd. That's interesting. Let me save you a little time over here. When we do this, invert and multiply, we're going to end up with 8/27 on the left-hand side. You can just trust me on that one. Calculate it later. But what about the right-hand side? Well done. R to the 3rd. The important thing to see here, and this is why we divided like this, is that we canceled out the a sub 1. So now we got a problem that just deals with r. R cubed. In fact, we have a pretty easy route to solve for r. What do you have to do to solve for r? Cube root, right? All right, so cube root of 8/27 is r. Not 3. How about 2/3? So 2/3, that's your r. All right, that's good. One down, one to go. So we got r here. We need to know what a sub 1 is. I'm open to suggestions. How are we going to find a sub 1? Plug it in where?
To one of the two equations that you gave.
Yeah, plug it in one of these two right here. Either to a sub 7 or a sub 4. I'm going to use a sub 4 just because it has smaller numbers. So a sub 4 was 12 equals a sub 1 times 2/3 to the third power. That's what this equation is saying for me. So it's 12 equals a sub 1 times 8 over 27. The fast way out of this one is to multiply both sides by the reciprocal. So 27 over 8. 27 over 8. And I think that's going to leave me with 81 over 2. And that's a sub 1. Yay. So we got both of them. We're in good shape. The final answer for this one is a sub n equals 81 over 2 times 2/3 to the n minus 1. Whew. Not bad. I guess the thing to keep in mind is that when you're solving these types of problems, you have two unknowns. You're going to need to give yourself two equations. And we got those two equations from a sub 4 and a sub 7. Any wrap up on this? Ashley, doing all right on this one? Let's try another one like that. Probably not as hard. That's going to be problem number 46. Here they give us r is 1/6. A sub 3 is 18. And we want to know what a sub 1 is and a sub n. So we want to know the first term and the general term. Well, the general term to start out with is a sub 1 times r to the n minus 1. But at least in this problem, I can do a little bit better than that. What could I write here at this first step without really doing much thinking? George? Thank you. A sub 1 times 1/6 to the n minus 1. Okay, good. So that really leaves me with one unknown here, which is a sub 1. Well, if I have one unknown, how many equations do I need? Just one. And I can try and get that one unknown if I use what I know up here. Try and plug in a sub 3 and see if you can get an equation that'll help us solve for a sub 1. let's keep in mind what we're told in this problem. We know that a sub 3 is 18. So I'll put that in here. 18 equals a sub 3. A sub 3 from this formula down here would be a sub 1 times 1/6 to the 3 minus 1, or that is 1/6 squared. Now what I want to do is I want to bring together these two parts, this one and this one. So it's going to be 18 equals a sub 1 times 1 over 36. If I multiply both sides by 36, then I get what? 648 equals a sub 1. Okay. So overall, your general term, well, that's your first term, so we got that part. Your general term is going to be a sub n equals 648 times 1/6 to the n minus 1. How are we looking on that one? Doing okay? All right. We can sum up geometric sequences in a couple special cases. We can sum up a finite geometric sequence this way. So, sum of the first n terms of a geometric sequence. There's a nice formula for that. First of all, the letter symbol here should be something you recall from our work in the previous couple sections. This is sum of the first n terms. When it applies to the geometric sequence, though, then there's a specific formula for it. It's a sub 1 times 1 minus r to the n divided by 1 minus r. That's really cool that we have this nice, neat little formula there. So let's put this one in practice, and with kind of a fun example. This will be problem number 88. So let me get that into our book. 88 talks a little bit about genealogy. So let's take a look at a sequence. That is, what's this little dot represent? You. Yeah, that's you. And then you've got a mother and father. And they each had mothers and fathers. So that's 4. And then if you go back 3 generations, how many people are there? 8. And if you look at the numbers here, what kind of a sequence are they forming? Geometric, right? Geometric, a sub 1 equals 1. So a sub 1 is 1. What does r equal? 2. Let's go 15 generations back with this sequence and find out how many ancestors do you have if you go back just a mere 15 generations. Okay, so we can do that. Well, we'll find out here. So basically what I want to find is s sub 15. And s sub 15, let's see, how come that's not a little crisper? There we go. S sub 15 is going to be a sub 1, which was 1. 1 minus 2 to the 15th power divided by 1 minus 2. Now, a lot of these you can simplify a little bit if you want to. I'm just going to type it in as is. So it's going to be, in the numerator, 1 minus 2 raised to the 15th power, and 1 minus 2 in the denominator. Look, if you want to realize, gee, that's negative 1, hey, power to you. It's no problem at all. Trying to simplify this before you write it in. Was anybody surprised by the result? Wow, are you guys getting the same thing? All right. There's a couple people, I'm getting a little doubt expressed here. So that's a 1, so I just ignored that. I just did 1 minus 2 to the 15th. Okay. All right. So, wow. 32,000. If you just go back 15 generations, that's a lot. And what's interesting is that it doesn't take you too long going backwards before you find that the number of your ancestors is more than the population of the planet. All right, it doesn't take that long at all. So how could that be? Your ancestors are, there's more of your ancestors than there are people living in the world. That's a good question. The answer is you're not genetically pure. That is, there's been a little bit of hanky-panky between your mom's side and your dad's side somewhere back in then, but it's not just a pure bloodline. It's not just like, all these people are strangers. Somebody was doing something with somebody else. That's what's going on there. So, all right, we won't get into that in great detail because this is a math class. All right, let's try a couple more along that line of summing up an arithmetic or summing up a geometric sequence. Let's take a look at problem 62. So what was it? 32,767. That's a lot. That's a lot of people. Problem 62 gives you a geometric sequence, although it's kind of disguised. It's disguised like this. It's the sum. My sigmas are terrible. It's the sum from k equals 1 to 6 of 10 times 5 to the k minus 1. Now with these things, it might not be a bad idea to write out the first few terms. You can even write out all the terms just to kind of convince yourself and see what's going on here. So at the first term, at k equals 1, let's see what I get. I get 10 times 5 to the 0 power. Well, 1 minus 1 was 0, right? Oops. Let's take a look at orders a beer. The second one says, I'll have half a beer. The third one says, I'll have a quarter of a beer. And the bartender says, stop, stop. And he takes out 2 glasses, puts them up on the counter and says, here you go. You know your limits. All right. Oh, come on, man. I had to wait an entire semester for that. It's not too easy to fill in some math humor. Whatever. I have to edit this before I put it on YouTube. I'll put in a laugh track there. All right. Let's do one last one, kind of like this. Let's see. I'm not sure if I want to do problem. Yeah, we'll do. How do I want to do this one? All right, the one last one I want to do is from the bottom here. Yeah, I guess problem number is 78. Does anyone remember what this bar notation means? 0.253 bar. Yeah, the 5-3 part is repeating. So this is 0.2, 5-3, 5-3, 5-3, 5-3, etc. Goes on and on and on forever. Never ends. Now the thing is, because it has a repeating pattern, it's a rational number. We can write it as a fraction. And that's the goal of this problem, is to write this, to figure out what fraction that is. Now I'm going to separate this into 2 parts. The 0.2 part here and the repeating part here. 0.053, 53, 53, 53. That part. So, okay. This part is 1/5, I know that. But here we're going to have to do a little bit of clever thinking. I'm going to think of this as 0.053 plus 0.00053 plus 0.0000053, etc. The next one would have 7 zeros. Maybe I should put that one. You want to put that one? Sure. So the next one has 7 zeros. 0.000000053, etc. This is an infinite geometric series. Infinite geometric series. And let's see if we can't figure out a few things about this so that we can sum this up. What would a sub 1 equal? 0.053. Good. And now here's a tougher one. See if you can figure out what r is. What is it that you're multiplying by to get from one term to the next? And take out your calculators and do it, or penetrate it with your great intellect. But figure out what r is. Don't shout out any answers. Give people around you a chance to figure that out. If you take any 2 adjacent terms, I'd probably stick with these two, 0.00053 divided by 0.053. What are you guys getting for r? 0.01. So 0.01 is really moving the decimal 2 places each time. Let's see if we can't sum that up using formula. S sub infinity is a sub 1 over 1 minus r, which is 0.053, divided by 1 minus 0.01. So it's going to be 0.053 divided by 0.99, and that's going to be 53 over 990. You can get that off your calculator. That's just this part of it. 53 over 990. Let's combine it with the other part. So I have 1/5 plus 53 over 990. 1/5 comes from the 0.2. I'm going to be lazy about it. Plus 53 divided by 990. And hit the answer to fraction key. And get 251 over 990. Now, if I were to give you a problem like this on a test, I have no problem with you guys using technology to check yourself, but I am going to want to see some of the work like we did here. For homework, try 9 through 35, 39 through 73, and 77 through 81 odds. Anything on 78 that maybe I went through a little too fast for you on that? Okay. Yeah, I want it written with fractions is what the goal is. And really, the goal is to sum up a infinite geometric series is what the goal is. I mean, there's kind of ways around doing it the way we did, but that's not my goal here. Okay. All right, good luck.